Hi, this is Indradeep Kumar, Assistant Professor, Department of Aeronautical Engineering, Institute of Aeronautical Engineering. First, I'm going to take the topic of aerodynamics. Okay, so today's class topic is basic concept of aerodynamics. So before starting the syllabus, we will see the important things what we will use on later stage. So that's why I'm starting with my first video from the basic concept of aerodynamics. So these things will be like concept of unit and dimension. So we will start from the basic itself, like what dimensions unit will be there. These things we will use. Then fundamental principles, whatever the fluid mechanics, then thermodynamics. So these things are required here. So I will start with those things from the basic, like from fluid mechanics, then thermodynamics, and then we will come to the geometrical shape like aerofoil, wings, aeroplane, how many types of aerofoils are there, how to distinguish the aerofoils, right? Then wings, then about the aeroplanes, and after that we will see the aerodynamic forces like lift, drag, these things are there. Then aircraft moments are also acting, some moments are there, so that we will see in this lecture. So we are starting from the concept of unit and dimension. So first, for defining anything, we require some, like we are measuring something. If we will go to buy something and we will ask, give me 2 gram, 2 meter, 2 kg. So right, for defining that one, definitely we need unit. If we will say 2, no one can give either 2 piece, 2 kg or 2 meter. So according to the quantity, we have to add the unit also, like 2 gram, 2 kilogram, 2 meter. Right, so that is the very important thing when we are measuring anything. And with that only we can distinguish how to measure. Like suppose if any solid item is there, we cannot say like give me 2 liter of salt. So those units are very important. So now the thing, unit and dimension, two different things are there. So just see here, dimension and unit. So how we will distinguish the dimension and unit? So when we are talking about the dimension, that is suppose we are taking the length. Okay, so here the qualitative concept of that is the length is what? It will be a linear displacement or distance as we will move like from here to here. So this should be the linear. Then from here to here, what length will be there? Okay, that we can measure. So now the thing we will measure here either in centimeter, meter, depending upon the length what we have to measure. So now the distance between 2 points. Okay, suppose from here to here. Now in this one condition is there from where we should start measuring. Suppose we can start measuring from here to here also, here to here also. So once we will take the reference, no, you have to measure from here only. You cannot measure from here, because if you will measure from here, you won't get the actual length or actual data whatever we require. So once we will fix the reference, no, this is the starting point, from here only you have to measure, right? So for measuring length, this reference is required. Now the next is unit. That shows like the specified amount of quantity, how much just in a starting itself mentioned, like 2 kg, 2 gram. So that is the specified, that fixed. In dimension, instead of this, we can change our reference point, this one, and then we can measure from here to here. But in case of unit, we cannot see. It's not like that. First you will ask, okay, give me 100 gram, and then you say no, from that you just remove 10 gram. So if they will remove 10 gram, means what? They will give you the 90 gram. It's not like that. First 10 grams they will remove, and the last, that is 11 gram to 100 gram they will give you. No, whatever the amount is there, they will remove that one. So in that we cannot change the reference in this one. But in case of dimension, we can change the reference, and according to that we can measure. So now just see some examples are there in what how we will measure. So in case of dimension, x meter. So generally length we are representing by capital L. What is that? A quantity of x meter has the dimension of length. So once we will represent by this one, okay, that shows it's a dimension and having the length, right, which is represented by x. So here this one is meter. So right now we are measuring in meter. Then next one is miles. So now our unit changed to miles. Means now whatever the distance will be there or length will be there, that we will measure in terms of miles. As you can see on the road when we are going, their road miles are there. So they are writing in miles. They cannot write their mm or centimeter because then many road miles will be required. So depending upon the length, how longer we have to measure, according to that we are using the unit. Now x meter to x mile. So do is just here x, we are measuring the same x and this x also, but unit is different. Here first one we are measuring in meters. Now this one is unit. Now this x mile and x meter are unequal quantity, but so we cannot equate like 2 meter and 2 kilometer. We cannot say both are equal. So for that we have to change that kilometer in terms of meter, and then we can equate the how much proportion that meter is there. But the dimension will be same because we are measuring the length. So unit will be different. Unit is miles, meters, but dimension, that in both the cases dimension will be same, and that will be in the, once we will convert miles into meter, that meter will be there, and hence the dimension of will be the x meter, either in miles or this one. So dimension still remains what as L only. Dimension won't get changed, but unit will change. Now come to the fundamental dimensions and unit. So fundamental means what? The very basic from which we can derive the other things. So there are 7 fundamentals. Dimensions are there. First one is mass, then length, time, temperature, electric current, amount of substance which is represented by mole, then luminous intensity, that is represented by CD, candela. So here we will use what? Mass, length, time and temperature. So these 4 units generally we will use here to derive the other quantity. So whatever we will derive from these 2, that is called the derived quantity. So by using these only we can derive the other quantities. So now derived dimensions and unit means from the using the previous one, whatever the fundamental quantities are there, we are using that one. So by using that we can derive these things. So first one is force. Like we are generally using what? Newton. So this is the dimension what? MLT minus 2. Then stress. This is also ML minus 1, T minus 1. Now just see here stress and pressure. This one and this one will have the same unit. Dimension also unit, also Newton per meter square, and here also Newton per meter square. Then the thing is why 2 different term? Why then we are using stress and pressure? So pressure is for liquid and gas, or you can say this is we are using for fluid which can flow, and stress is for the solid substances. Solid substance we cannot say that pressure. Now the thing, what is pressure? Pressure is nothing but how much force you are applying per unit area. Suppose in 1 meter square, how much force you are applying, that will give you the pressure. So now from suppose if you want to find force, then force will be what? Pressure into area. Now by using this only we can derive this quantity that I will show you later. Next, energy or work. What is energy? It's the same. From the energy or work having the same unit, same dimension. So their unit dimension is ml to t minus 2, or you can say ml power 2 t power minus 2. So these are the way how to represent dimensionally, and this is the unit what we are using. So when we are even in numerical also we are finding, or when we are expressing, these things are very important to mention there. Otherwise we cannot say either 1 gram is there or 1 kg is there or 1 kilometer is there. Depending upon the quantity only we have to use these things. If we will not use this unit, it's insignificant what is the, how much quantity is there in what you measure. So we require them, that means definitely we have to mention these things. So now then moment and absolute viscosity, kinematic viscosity. Well, so these are some examples which we will use later. Now the thing, how to get these dimensions, right? So let's see that one. So now just see the example, force. Force is what? F equals to mass into acceleration. Right. Now we have to change this one. So from here we are finding this one. So now just see, mass we can write as capital M. Now acceleration is what? What is acceleration? Rate of change of velocity, or you can say velocity by time. So put here velocity by time. Now you have M into V by T. Now the next, mass just keep as it is, because what we have to do, we have to convert all the quantities whatever we have in terms of the fundamental quantity. What? Time, length, mass, in those terms we have to convert. So still V is not in the fundamental quantity. So we have to change this V also. So now V, velocity is what? Distance or displacement by time. So now V will be equals to L by T. So this is V, and then this time. Right? So this is into. Now what happened? M into this becomes L by T square. Right? This T and this T will get multiplied. So now L by T square. So now can we write this as M, L and T square. I am taking this denominator to numerator. So that become power minus 2. Here power 2 is there. So going to numerator, that becomes minus 2. So now what will be the dimension of force? ML T minus 2. Clear? So now from here you can find the dimensions also, like, so now let's see, force. Generally force, in previous slide also I showed you. So force we are measuring in Newton. So 1 Newton, let's see both sides it's the same or not. So 1 Newton should be equals to what? Here M is what? Mass. So mass should be in kg. Right? L is in meter. So kg meter. Right? Now what is T? Second. Power minus 2. So kg minus 2. So means 1 Newton we can represent in terms of kg power m minus 2 also. That is kg meter per second square. Like this we can. Now one more we are saying for pressure or stress. Having same just when we are using either in case of solid or fluid. So now pressure, just I derive pressure is what? Force per unit area. So now force is what? So just now we derived for force. Either you can use that one, or again start converting everything into the fundamental quantity. So what was force? Force was mass into acceleration by area. Now mass, acceleration is what? V by T by area. This we can write again, change V. So M into V is L by T by T, and this area is what? Meter square, that is length square. So here I am writing L square. So now just see here what? M, then this L, then this is T minus 2, that already we had seen, and by L square. Right. So from here what happened? This L will get cancel. So from here what we will get? M, L minus 1, T minus 2. So this is unit of force. And same here from we can derive here, this is M. M is what? In kg. L is per meter because it's denominator, per second square. So you can say that is pressure is equals to kg per meter per second square. So this will be the unit of pressure. Similarly, you can derive for other. So your assignment is whatever the remaining are there, right? These are I derived for force, the stress or pressure. Remaining things you can do as an assignment. Now come to the definition. So let's start with the pressure. Just I derived pressure is what? It's a force per unit area, or force divided by the area. So force unit what was there? Just now we derived MLT minus 2. Area is L square. So once we will divide, what we will get? ML minus 1 T minus 2. that we derived. Similarly, so P is force into area. Now here divide length by length. Okay, we can divide. Why? Because L by L, that will cancel and it will remain 1. So we can divide and multiply L by L. So now after this, what happened? Can we write this as F by L into A by L. Now force, what was the formula? MLT minus 2 divided by L. Similarly here L square by L. So now with this, what happened? ML, this L into L square becomes L cube T minus 2 by L square. Right? So now we are dividing here. We got in terms of force. That is pressure in terms of force. Now in terms of, if suppose energy and volume you want to change, like this one here. Energy divided volume. So just see. Pressure is force into length. Here just we multiply force into this length. So overall what we will get? ML to T minus 2 divided by ML divided by L cube. What is L cube? Volume. ML to T minus 2, you see here, unit of energy, ML to T minus 2. So for this, what we can write? This as energy and this is volume, right? So now energy divided by volume, and that is called energy per unit volume or energy density. So in terms of energy density also we can define the pressure. Now next is temperature. So what is temperature? How you can, generally we are measuring temperature by using the thermometer or any temperature measurement scale. But how they are having the temperature? Okay, so it is just because of the collision of their molecules. So what happens when molecule collides? They possesses the kinetic energy, and that kinetic energy provides, or you can say sense, in terms of the temperature. So that kinetic energy only we are sensing, either solid, liquid or gas, whatever is there, as a temperature. We can use temperature, that is dimension, Kelvin, centigrade, degree Celsius and degree Fahrenheit, depending upon our requirement. Now the next is density. Just now here, this we are energy by volume. So that becomes energy density I told. Similarly here, when it's the mass by volume, okay, this will give you the density, or you can say mass per unit volume. So same, what will be the unit? Mass is kg, volume is LQ, that is LQ or meter cube. So if you will write in terms of dimension, then it's a meter cube. So kg per meter cube is the unit of volume, sorry, density. Now in terms of this one, so mass is m, volume is LQ, dimension. So this becomes ml minus 3. So this will be the dimension of density. Now viscosity. This term is very, very important for the aerodynamics. Right? Generally what happened? We are not able to see the air, or when the speed of the air is too high, then only we can feel okay, air is flowing. But if anything is moving, then they are experiencing some force. That force is just because of the air, right? Even on the road, if you will move, then you can feel, okay, something is coming towards us. But though if normally you are standing, then you won't feel any forces there. So how that will be there? This, like in case of fluid, when suppose in container fluid is there. Why in container is there? Why not it's flowing? If suppose you will drop here some water, what happens? Slowly it starts, it's not suddenly, it will starts moving. So how they are moving, based on that only, that which type of surface is there, which type of surface is there, according to that only you can see. So let's see, tendency of a fluid to resist sliding between layers or rate of change in shear stress. So what is that? Sliding between layers. Just now I told on the surface, if it's there, then what happens? Once we pour the surface, and if surface is very rough, then it will be there only. If surface is very smooth, then it starts sliding slowly. So how it's sliding, then what happened? Water is there, so some water is still stick in that one. So after that what happened? Once water gets slide slowly, it moves and finally it's get over. But and in the case of like tiles is there, you can see tiles having the very smooth surface. So there water can move easily. So some water stick on the surface of the tiles also, and even the generally rough surfaces there also. Now there are two types of viscosity. One is dynamic, another one is kinematic. So first see what is the dynamic viscosity. Dynamic means what? Generally when it starts, something is moving, that time we are saying it's dynamic viscosity. Let's see. The dynamic, or it's a coefficient of dynamic. So generally we are measuring in terms of coefficient of that one or the exact value of that. So let's see. Dynamic viscosity is a direct measure of magnitude of the viscosity of the liquid or fluid. So what is magnitude of the viscosity? Means by what amount it will stick on that one, means how much it's aligned. Just like so if it's a rough surface is there, the water molecule or liquid molecule will stick more. If smooth surface is there, it will stick less. So now just see how these things are there. So for that we are considering here two layers are there, two surface. Now this one is just kept, this as one as fixed and another one moving. Now if suppose water is there, so let's see, two parallel plates placed a distance h apart, right? So here h and h is there, so it's a distance. Now in between just water is filled or any fluid, that is not necessary that water, depending upon how much viscosity is there, that you have to check. Water have less viscosity. If suppose you will put honey will have more viscosity, then it won't allow that much. So that depends on that. Okay. Now is to apply a force on any of the surface, either this or this. Only one surface, keep another surface and rest. So now once we'll apply the force on any of the surface, what happen? It will start moving with some velocity. Now that velocity, suppose that velocity or speed is v. Okay. So now let's see, the speed of fluid will vary linearly as shown in the figure. But what happened? This, whatever the contact of this one is there, here you can see at this, if suppose this plate is moving, this part will be there, but here this part will move the farthest one, right? This what? Here the fluid molecule will move up to this distance, but whatever is here, that is moved very less. So overall you can see it's a varying linearly, that straight line is here, right? So this varies linearly. Okay, and according to that, so this molecule here, just compare at this point and this point. This water molecule or fluid molecule from here to here it moves, but this one is still here, right? So this is just because of viscosity. As closer to the surface is there, that will resist that much. As beyond the surface is there, that will move easily. Now just see. So how we can find that one? So just now we had seen what is this one? Force by area, that is pressure, right? So now just see here. If the area of fluid in contact with each plate is A, means what? In this figure here, whatever the area is there, that is how much water or fluid molecule is in contact, that is A. Okay. So what will be the shear stress? As I told you, that force per unit. Here is stress. Now the thing, why stress we are considering here? Though it's a fluid, then why we are taking, instead of pressure, we are taking here stress? Why? Because we are counting in terms for, we are finding for the solid surface, with the solid surface, and solid surface only they are in contact. So now the rate of shear strain. Strain is what? Rate of change of length. Suppose now area is there. So now this is there. Now what is real shear strain? That force per unit area should be there. So now here in terms of this we are finding shear strain. The strain is nothing but just like suppose this area is there. Okay. Now in this area, how much, if suppose by applying force or something by this amount it's increased. So the how much amount it's increased, divided by the total is called the strain. So here, because of the shear force, strain is developed, so that's why we are seeing as the shear strain. So because of what? Upper plate. How far it is? That we are seeing at h distance, right? So now the shear stress will be volume by the distance between the two plates. So now from here one term arises, that dynamic viscosity coefficient, that which is represented by mu, right? So that coefficient will be here. So this pressure and this overall pressure, right, should be equal. So from here we can say F by A, that is force per unit area, will be equals to mu into V by H. Now from here we can find the value of mu. So from here mu will be what? F into H by A into V. Right. Now what is F? Just now we derived M L minus 1 and T minus 2 for this one, and then what will be the equals to V, velocities we can find here for velocity and height. So what will be the velocity? L T minus 1, okay, and height is L minus 1, right? So these two sides should be equal. So from here we can say mu equals to M L minus 1 T minus 1 will be the unit of viscosity, that is dimension of the dynamic viscosity. Now come to the second type of viscosity, that is kinematic viscosity. So what is that? When this is there, dynamic viscosity divided by the what? Density. So just whatever the dynamic viscosity is there, or you can say dynamic viscosity per unit density is called as the kinematic viscosity. So kinematic viscosity is represented by mu equals to what? Kinematic viscosity mu divided by the rho density of the fluid. Now bulk elasticity. So it is a measure of how much a fluid or solid will be compressed by the application of external force. If suppose we can compress something, so based on that only we can say, okay, this one having that much bulk elasticity. Like suppose iron is there, we cannot compress iron more. But at the same time, if a sponge is there, we can compress too much. So based on this one, like water is incompressible fluid, but we can compress slightly of that one, that very lesser amount of water we can compress, but still we are considering that as an incompressible fluid. If suppose we can compress, like gas is compressible, we can compress and we can convert into water, like deodorant you are using, that is the compressed gas in the form of liquid. So at very high pressure we can compress that one, but suppose solid is there, that we cannot compress. So based on that, how much we can compress, they will have that much the bulk elasticity. So what happens when we are pressing the deodorant container, that is coming out in the form of gases only, not it coming out in the form of liquid. So that means whatever the pressure is there, we are releasing that pressure. So they are coming back again to their original form, and that is only the elasticity. When like suppose rubber is there, we are stretching that one, so that got stretched. Once we will release that force, what happened? Again rubber will come back to their original position, whatever the original shape, size is there in that one. Till that, but if suppose we will stretch more, okay, that might be possible that rubber band itself got broken, or otherwise some stretch will be there, just like balloon. If balloon, you can see in the starting it's of very small size. Once you will blow the air inside, that becomes the bigger one, and after releasing those air, still there some deformation is there, they won't come to their original size. So that is the beyond the plastic limit. If you will fill air in the balloon also, till their plastic limit, their deformation won't be there. So now let's see. If a certain small volume V, now just we are taking the very small volume of fluid, is subjected to a rise in pressure delta P. So now what we are doing, whatever the pressure generally they are experiencing, or because of atmospheric pressure or anything, in that we are changing the pressure by a small amount, that is delta P. because of what happened, we applied more force, so now the volume will decrease. So volume will decrease means what? Now that by delta V, volume will decrease. So here negative sign shows decrement in the volume. So now volume will decrease by delta V, but just minus sign is there to show it's decreasing. Now the volumetric strain, as we have told you, volumetric strain change in volume by the original volume. So by what amount volume is changing? Delta V. So what? That is delta V. That is minus delta V is because of decreasing volume. And what was the original volume? V. So this is the volumetric strain. Right. Now just we have to use these two concepts, right, to derive this one. So now just see, K is the bulk elasticity, right? Change in pressure, because of the pressure only what happened, they experience the volumetric strain. So pressure by volumetric strain will give you the bulk modulus. So pressure is delta P, because we applied delta P pressure, a small pressure we applied, and because of that they experience minus delta V change, that is by a small amount of volume got changed. What is the volumetric strain? That is minus dV by V. So change in pressure divided by the volumetric strain, that is minus dV by V, will give you the bulk elasticity. Now what we can write from here? This becomes minus delta P by delta V and into V. Or this V you can write here also. So minus V delta P by delta V. So this is the bulk elasticity formula. Right? Now what happened? Just see here. This is V. This is also V. So V having either change, a small change or bigger change, that must have the same unit. That is volume is, if suppose this is in meter cube, then this is also in meter cube. Meter cube divided by meter cube get cancelled. Means volumetric strain having no unit. So this is unit less quantity. So now this is unit less quantity. So whatever the bulk elasticity will have the unit, that is same as the unit of pressure. What is the unit of pressure? ml T minus 2. So hence K will have also unit as ml minus 1 T minus 2. So this will be the unit of pressure, or you can say as well as unit of bulk elasticity. Now this one comes to the thermodynamic property, because that also affects as you move. Even you can see that as you move higher, that their temperature changes. So temperature changes, then how temperature changes, based on that how temperature affects, right? These things we have to consider. So now we will see some thermodynamic property. So first one is specific heat, right? Means by raising the temperature, how much the amount of heat can be raised or required. So the specific heat of a material is the amount necessary to raise the temperature of unit mass. Means unit mass, one unit mass is there. Either you can take 1 kg. If you are taking 1 kg, then according to that you have to take the other things also in the same unit. So 1 unit mass of the material by 1 degree. Means 1 unit mass, how much heat is required to raise their temperature from 20 to 21 degrees Celsius. Now suppose 20 degrees Celsius some material is there. Just start heating. Up to what it will reach to 21, you have to calculate the total heat. How much they require the heat. That is your specific heat. So to just, in simple word, to just rise 1 degree Celsius temperature of 1 unit substance, how much energy is required? That is your specific heat. The dimension is L2 T minus 2 theta minus 1. Now just see here theta as temperature. Why? Because per unit time is required. So once time will be in denominator, so once we will write, this becomes theta minus 1. And the unit will be in SI unit, joule per kg per Kelvin. Same here, like L2 T minus 2, okay, and here. So joule per kg per Kelvin will be the unit of a specific heat. Now there are two types of specific heat. First one is at constant volume. Means what? Just keep the volume constant. Don't allow to change the volume. Second one is at constant pressure. So now pressure should be constant and the other things you can change. So when volume is constant, then what happened? the amount of heat, same here, we are finding for heat, how much heat is required, means by keeping the volume constant, we should not allow to increase the volume or decrease the volume. Both are not allowed. Then the total amount of heat required to raise 1 degree temperature, that is called as a specific heat at constant volume. Similar way, keep pressure constant. It should not increase or decrease. Then how much energy is required to raise 1 degree Celsius temperature, that is called the specific heat of whatever substances they are, that one at constant pressure. Now, so first we'll see a specific heat at constant volume. So let's see, internal energy we are representing by a small e. What is that internal energy? Because of the internal molecular collision. Because of that only they possesses the internal energy. So internal molecular energy means what? Because of movement of the molecules. Movement means what? Kinetic energy. When anything is moving, they must have the kinetic energy. Why? Because they have the mass, and now movement means velocity. So kinetic energy means half mv square. Mass, that must have, that particle is having mass, atom, and now it's moving inside, our collision is there, so because of this. So by this amount only they will collide. So they have the kinetic energy, right? How much kinetic energy is there? Based on that only they will have the, because as much as they will fast, they will absorb the energy and their velocity will start increasing. They will collide faster. They will collide faster means they require the energy, they absorb the energy, now they are moving faster, and because of that their temperature starts rising. So then what happens? So internal energy must be equals to what? It should be this one, Cv into T. How much specific heat and time, for how longer the temperature rises there. So this one, internal energy is E equals to Cvt. Here Cv is the specific heat at constant volume, right? So from here you can find Cv is delta E by delta T, or rate of change of internal energy. No, not rate of change here. This T is temperature, not time. So don't confuse with temperature and time. When we are writing T, capital T, that is the temperature, small t is the time. So delta T is not the rate here. Delta small t is there, then it will be the rate. Here, change in temperature. So change in internal energy divided by change in temperature is only the Cp. Similarly here, because of pressure, so that time what we have, the total energy is required. Now in this case, so total energy is what? Sum of pressure energy per unit mass. That is only what? Enthalpy. So enthalpy means just enthalpy is Hcp dt. Cp is here coefficient, that is a specific heat at constant pressure. So again similarly Cp keep one side, T take another side. So that becomes H by T. So Cp is H by T. So more generally if you want to write delta H by delta T, that is change in enthalpy by change in temperature. So Cp is change in enthalpy per unit change in temperature. That is just in the starting itself we had seen the definition by increasing 1 degree Celsius. So how much enthalpy will change for changing the 1 unit temperature? That is called as Cp. Now ratio of those two, that is a specific heat at constant pressure and a specific heat at constant volume, that is defined as gamma. Okay, so the ratio of a specific heat is a property important in high speed flow. Just see, this is very important for us. Why? Because all the aircrafts are flying at very high speed. So it's defined as the equation like gamma, a specific heat ratio, that is called as, right, Cp by Cv. Generally for air we approximated, actual value of this is 1.421 something, but we are considering only 1.4 as the gamma value. Next, just we discuss enthalpy, right? Enthalpy, what was that time? Here, enthalpy is Cp into T. So just see how this is there from here. Enthalpy of a unit mass of gas, here just see again unit mass, that is very important. Otherwise, the mass also should be there. Is the sum of internal energy and pressure energy. What is pressure energy? Just we had seen this one. So pressure energy is nothing but P by rho. Right? So from here enthalpy will be what? Sum of internal energy. We used internal energy as a small e. Pressure energy as P by rho. So sum of internal energy plus pressure energy. What was E? We just used CVT. This is as P by rho. H was what? CPT. Just now we had seen this one. So put these things. So what we have? H equals to CVT plus P by rho. Now I am writing for H also. H was CPT equals to CVT plus P by rho. So this is, you can say, the enthalpy formula in terms of specific heat at constant pressure and at constant volume, and then what? Pressure energy. So here just see what terms are involved. CP, CV, CP, temperature, how much temperature increased, then pressure and density of the fluid, or you can say the pressure density. Now next is entropy. Entropy is nothing but just change of or order of randomness, means how fast it's like. Suppose after absorbing the energy, what happened? I told you that kinetic, they possesses the kinetic energy. Because of that, their randomness will increase. So once randomness will increase, it's not like that they are moving whatever like this, they are moving. So they will move faster. No. Instead of like this is then suddenly then like this, that movement will be there. So now what happened? This is not in the particular order. So now that becomes disorder. So that's why it's the disorderness of that substance. By what amount it's increased, that is the entropy of that substance, or you can say just randomness of that substance, system, or whatever you are considering that you are finding their randomness. So entropy is nothing but just change in energy, that is delta Q, by the temperature. That will give you, so means by providing the temperature, how much energy change is there, that will give you the disorderness or entropy of that substance. Now come to the original, what we required as a aeronautical definition. So we are starting from aerofoil geometry. So now just see, first start with this one. Here you can see this is the same, right? And both side at upper from here and lower side, you can see it's the same. If that is there, then we can say it's a symmetrical. Generally we are say whatever, if suppose this axis is there or line is there, from this line this is there and this is there, then we can say it's a symmetry about this line. Similarly here, this is symmetric about this one. Now what is this one? What is this one? These things we will see here. So now this is what? From this line or axis, okay, go here. So every point you can see from here, suppose now from here to here you will measure. The same will be here to here. This distance also will be same at every point. If at every point it's the same, then we can say it's a symmetrical about that point. If it's not same, like in this figure, so just see here, from here to here it's very less, but from here to here it's too big. At every point you can see it's a different. So this is not symmetrical. That is named as cambered aerofoil. Another thing, what is cambered? Now once cambered aerofoil is there, so definitely that camber should be there, right? So now let's see. When these distances are not same from the camber line or this one, okay, then we can say that foil is cambered. If the distance is same from this line, then we can say it's what? It's a symmetrical aerofoil. Let's see. Camber. At any distance along the chord from the nose, a point may be marked midway between the upper and lower surface. You can mark anywhere, either this point, this point, this point, this point. Anywhere the distance must be same. If everywhere it's the same, then only that will be this one. The locus of all such point, which is usually curved, is the median line of the section and is called the camber line. Means what? It should be the median. Now just see how. So median means what? It should be always a straight? No, not like in this one. Median means you have to take average of this one. Like just see here. In this point you can see this distance is there at the upper edge. But now at the lower it's a smaller. After this is bigger one and here a smaller. Move this one. So this is not the cambered line. Right? This dotted one is the cambered line here. Right? So means we have to measure all the distance from this to this only. Right? From here to here. Here to here. This one. So don't confuse with the cambered line and chord line. Chord line also I will tell you later. First see this dotted line is the cambered line. So now from the cambered line, the distance should be mean of that one. Means just whatever the shape is there, like suppose this shape is there, right? Take median of that one. That should be the median line. That is only cambered. Now, one line that join the leading edge to trailing edge. That is again leading edge to trailing edge line, right? Line means what? It should be a straight. It should not curve like this. Cambered line can be curved, but this should be a straight. That is called the chord line. Now, in this case, because it's a straight line, here this one is curved. Here, this is a straight. So, in case of symmetrical aerofoil, cambered line and chord line both coincides. But in case of unsymmetrical or cambered one, both will have at a different place. So now, thickness distribution. So thickness means what? How much is there? So from here, you can see distributed it's evenly from this cambered line or chord line. But in this case, you can see from here, this is a chord line here it's more above this line. Just see here, from here to here it's there, but in this case it's a very less. So how much thickness is there above the chord line, below the chord line? That is the thickness distribution. If thickness distribution is uniform throughout above and below the chord line or cambered line, then we can say it's a symmetrical aerofoil. If it's not, then we can say it's cambered aerofoil. Now, wing geometry. Geometry stands for what? I mean, how the wings look like. Right. So now just see, this is the view of actually the top view. You can say this is how wings look like. So now, the plan form of a wing is the shape seen on a plane, right? That's why plan form, Miss Fala. When we are forming anything or we are planning, so that is the plan. So by seeing from the top how it's look like, that is this way. Or you can say the top view of this is the wing. Now here also some dimensions. So from here, this one, from this point to this point, okay, that is named as B, that wing span. This is the center line, okay. So this distance must be what? B by 2. B by 2, that will definitely it will divide by half. This rear part is the trailing edge. This is the leading edge. If this will move the direction of flight, the direction of flight should be this side. Then only this will be the backward side, and backward side is the trailing edge, and front one is the leading edge. The edge of this side, this is called the wing tip. This is wing, right? So this is wing. So at the tip is the wing tip. So wing tip, that is the chord length of the tip. This is CO, chord length of the this root. That feels like how much is there, that length. Now, so let's see the chord here. What will be the two length CT and C0 are the tip and root chord. I told this is tip chord, this is root chord. So these two, when we will measure, that is the chord. So two types of chords are there: length, that is tip chord, and root chord. Now what is root chord? Distance between the intersection with the fuselage center from here to till the trailing edge. That will give you the what? Root of the or chord root. And what will be this one? From here to here. This will be the chord of the tip. The ratio of these two is called the taper ratio means CT by C naught. By taper ratio means what? By what amount it can be tapered. So just see here. This is the what is connected to the fuselage. So from here and by what amount it should be. It's not like that you can do like this. No, here just see the tapered is very. So how much you can tapered, right? That proportion is called as the taper ratio, and that should also be uniform. That's some certain particular measurement. It's not like that by whatever amount or anywhere you can. It's not like that like this. Oh yeah. So now from here it's tapered up to this, and suddenly you increase like this. No, if this will be there, then again some forces will be here and here. That won't be the perfect one. So by this taper ratio only decide how much the length of the chord and length of the tip should be there. So for most of the wing, this CT by C naught should be less than 1. Now wing area or the platform area, whatever is here. The platform area of the wing is what? Including the fuselage, whatever they combined, and the gross wing area or wing area. That means simply we can say that is the gross, the total area. It's not like that this part only. This also should include. So this is the total, whatever the curve is there, that is the, or you can see the wing geometry, that is the total area, and this excluding this part, that is this one, wing aircraft part, that is the what? Plan area. So just see here, the platform area, exposed wing, that is the outer, which is not inside the fuselage here. So excluding this one, so this total is the gross, and excluding this one is the platform area, is the net wing area. That means the total area of the wing. That should not be, that should not included the area inside the fuselage. Now mean chord. So that is very useful parameter. By that only just now I explained that should not be tapered in that particular ratio. So or it's the what? Mean chord or geometric mean is just simply denoted by what? Here C bar, which is equals to S, that is the platform area divided by the V. So S by V is the mean chord. So with this we can find the mean chord of the wing. Now aspect ratio, this is very important one. So that is span area, that is span square divided by area square. So what is that? B here, span area by span. So here just reverse of that one, but this should be the B square. So span square divided by the wing area. That will give you the aspect ratio. So now let's see. This note you have to remember. For rectangular wing, aspect ratio will be equal to what? B square by C. Now why? So let's see. AR is what? B square by area. Area is what? Length into chord. So B into C. This B will get cancelled. That is B by C. Right? Why? Because S is BC. So for rectangular one, AR will be equals to B by C. Now wing sweep. So it depends on like how much angle is inclined. Now just see here. It's not horizontal one. It's inclined by some amount. So whatever the inclination is there, that is only sweep. So in both the side you can say the wings are not horizontal. So by what amount? That is inclined. So let's see. The sweep angle of a wing is that is means in between the angle of this one. A constant from here, this chord line, now how much angle they are forming, that is that. Okay. So this is denoted by what? Yeah. This one. Inverted V you can say. Okay. Now there are two types, sweep back and sweep front. So just here. Sweep back is commonly measured on the leading edge. Okay, so that's why what we are, this one, delta, that is inverted V, so inverted V at leading edge. Now on the quarter chord, what happened? Just that should be the 1/4. Quarter chord is at 1/4, and trailing edge, it's a V E. So at every distance, we will see in the next figure how these things are there. Yeah, these will be there for 1/4, that will come to later. Now the dihedral angle. So if an airplane is viewed from directly ahead, it is seen that the wings are what? Generally not in a single geometric plane, but instead inclined to each other. Here, just I told. Okay, at a small, that angle is very, very small. It's not like that around 10 degree, 20 degree, 15 degree. If you will see properly or consistently, then only you can observe, oh no, these wings are inclined. Right. So the total, let's see. Small line. Imagine line drawn on the wings along the locus of intersection between the chord lines and the section leading edge here. From this chord line, this is right, and the center of this one. So then from this chord line to this one, whatever the angle is there, that angle is 2 tau. And if 2 tau is there, then we can say it's a dihedral angle of the wing. So see, if the wing is inclined upward, then they are said to dihedral. If its wing is like this one, downward, then we can say this as anhedral wing type. Now incidence, twist, washout and washing, these are the terminology which we will use in later stage. So what is incidence? When an airplane is in flight, that is, it's moving, the chord lines of the various wings sections are not normally parallel to the direction of flight. That time what happened, just we had seen in this image. These are not parallel at that time, right? So that is called at that time, that is the incidence. Next, the angle between the chord line of a given aerofoil section and the direction of flight or the undisturbed stream is the geometrical angle of attack. Now just see here, undisturbed stream. This what? This stream should become, this stream should not deviated. Then whatever the angle they will form, that is called, like here aircraft is coming, right? So the angle between either or the wing is there, then angle between this streamline and the chord length of this one, whatever is there in that angle is called the angle of attack. By that angle only the air is hitting to the wings or fuselage of the aircraft. So that angle is very, very important. That angle, as much as that will be lower, they will experience that much lower gust. Now just see, the concept of incidence to the twist of a wing, it may be said that what? If the geometric angle of attack of all sections are not the same, the wing is twisted. Means what? Here, if from here, this is chord line and this is angle. So whatever you will measure, you can see the same angle will be there. Now instead of that, what happened here? Right? Now just take this one. Instead of this, now take like this. So see here, if you will measure this distance, this angle definitely will be more compared to this angle. So now angle is not uniform. If angle is not uniform, then we can say that wing is twisted. Or anything, if two things are parallel, you can say that everywhere the angle is same. But just now one's twisted. Now up to this, the angle will be same, and now here the angle will be different. So once angle is different, we can say that is a twisted wing. Now next is, if the angle of attack increases towards the tip. Now here, this one, whatever the wing shape is there at the tip, if it's increasing, then we can say wash in. If it's decreases towards the tip, then this is wash out wing type. Now the aerodynamic forces. First one is lift. So now let's see lift here. Lift, weight, velocity in this, it's moving, and another one force is acting backward of this one, that is called the drag. Now the thing, this lift force helps to move up to the aircraft. Because of this only it's moving upward direction. This will help to move forward direction. It's not like that once aeroplane will move up because of lift and that will stand there. That should move also forward. So this V helps to moving toward, that is called the thrust. And one force acting backward side, that is called the drag. Because of that only they are experiencing the lesser lift, or you can see the decrease in velocity. So this should be as minimal as possible. We are always trying to reduce this drag force. Now the thing is, why drag force is there, that we will see, and how many types of drag forces are there and how that is producing, that we will see in next slides. So now one thing, just remember, just see here, in this case, when the steady level flight is there, right, this wing, that is lift and weight of the aircraft are coincides, that is in the same direction, equal opposite will be there, right, because of that. So this will balance by the weight. But when at the time of climbing, always weight acting vertically downwards, weight never acts incline this one. So it's not like that, okay, lift is here, so weight will act like this. No, this is wrong. Always weight will acting, that is W, which is equals to what, mg, always acting vertically downward. So now the thing, how this lift will balance, the vertical component of this one, of this weight, that is mg cos theta, will balance by the lift, and because of that only this will move up also, and they will have the velocity, so they are moving forward also. Once it will be again in the coming downwards. Now just see here, this one, bank 1. So now this again, just see here, in every case weight will always act vertically downward. So this is the case of high speed, in that case it's coincide. This is the case of low speed level flight. This is, that is, while the climbing also you can say, and this is the banked circling flight, when the flight is turning, and that time though lift should be there. If lift won't be there, then flight will come down. At that same height we have to take turn, that is, that flight should take turn, this, that lift must be there, and weight also will act. Now this just component will change. Now instead of this side, now that lift will balance by this component of weight. Okay. So now the another force is drag. That explain about the drag. This is the backward force, which prevents the motion of the aircraft, or you can say lift of the aircraft. Now side force, the forces acting on the body of this one, or you can say the drag, that also comes under the side force. Now aerodynamic moments. So now when the force is there, and definitely from force, where at what point it's exerting, moment will be there, right? So moment is what, force into perpendicular distance, that is only the moment. So wherever the force will act, like suppose when you say up, so if force will act here, then from here to till where is the this one, definitely that much moment will be there. Suppose this is 1 meter, so force is acting here, so force into 1 meter will be the moment of this point here at half meter. So force into half meter. So as you move to the fixed part, according to that the moment will change, and by changing those things only we can take the turn, roll, and move. These things are there. So first one is pitching moment. So in this lift and drag, both are there. So this when vertically plane, when the aircraft is flying horizontally, like this is flying, right? Then what happened? Suddenly needs to move up and down. Like while moving up, then it's required. Then coming down, so that means you, or you can say at the time of takeoff, that pitching moment is required. Now the rolling moment, when you have to roll, means what? It's just like rolling this one, right? So means you have to take, you can see when you will fly, sometime left wing will go down and right wing will go up. So left is coming up, means right will come down. So that type is, or just here. So this is the rolling one. Now yawing one is taking left and right turn. So this will give you the yawing moment. Now the one of the important thing is center of pressure. This where we are assuming the total pressure is applying on that one. So let's see. The aerodynamic force on an aerofoil section may be represented by lift, drag, and pitching moment. This already we are seeing. Now what happened? From where these things will be zero, right? or you can say in another word, where the pitching moment, coefficient of the pitching moment becomes 0, that point is the center of pressure. So why the center of pressure is there? Because as we had seen, I told you here, at the distance of this one, their moment will change. So definitely at some point, at this wing, one point will be there which is not experiencing any moment, right? The point which is not experiencing the pitching moment or moment, that is called the center of pressure. Let's see. Lift, drag and moment acting at the aerodynamic center. So these all are acting at the aerodynamic center. So means what? If suppose this is acting here, so this is the aerodynamic center of this one. Or you can say this is the aerodynamic center. Right. So here, lift and drag only acting at the center of pressure. A fraction KCP of the chord behind the leading edge. So lift and drag acts at the center of pressure. Why? Because their pitching moments is 0. Now come to drag. This is the final one which I told you we will see at the later stage. So how drag is there and who is there? It's not like that some people is there and who is forcing backward. No. Because of the air, only aircraft experiencing some backward force. Right, or you can say the shear force or viscous shear, right? And that is only the drag which prevents the movement of the aircraft. Now that also of different type depending upon where it's generated. So it's totally dependent on what? Because of the air, right? How air hits the aircraft or air acting on the aircraft, based on that only the drag is generated. So first one is, let's see, we are seeing the total drag, means overall the whole body how much drag is produced or how much drag they are experiencing. Let's see. Total drag is formally defined as the force corresponding to the rate of decrease in momentum in the direction of undisturbed external flow around the body. Again here what is the undisturbed external flow. Once this flow will disturb, we cannot say because of that only this one is there. Whatever we are measuring, that should be something in case of reference or uniform, it should be there. So that's why the flow should be undisturbed. Then whatever they will experience the moment, that will be there. Or in another word also we can say it's the total force or drag in the direction of undisturbed flow. Whatever the force they are experiencing towards the undisturbed flow. In another word, you can say sum of pressure drag and skin friction drag. Now the thing is, what is skin friction drag? That we will see here also. So drag, because of once what happened, air flows over the surface of the wing. So because of that also they produces the drag. So because of the skin of the aircraft, whatever the drag is produced, that is called the skin friction drag. Let's see. A skin friction drag is generated by the resolved component of the traction due to shear stress here. Right? The shear stress acting on the body of the surface, means whatever is there, shear what? Along the surface only that will move. So this is the shear one, right? So on the surface, how much drag is produced because of the air? That is called the skin friction drag. Now next is pressure drag. So pressure drag is generated by the resolved component of the force due to pressure acting normal to the surface at all the points. So let's see a pressure drag, that is the normal of this one. How much force is acting on that one and all the point of that. So that will be, or just you can say the pressure like here, air is hitting like this. So because of this, how much they are experiencing the pressure here. Okay, that is the pressure drag. It's not like that always all the air stream will come surface to the surface only. Some will hit like this also, inclined also. So how much, because of this air stream, they are experiencing the pressure, that is called the pressure drag. Now induced drag or vortex drag, that induced at the, in case of 3D geometry only it can be induced. It's not in 2D geometry. Why? And it's at that induced drag, means because of the at the tip, even you can see in aircraft, the tip is there like it's somewhat, it's a bending like this at the tip of this one. Sorry, at the, yes. Okay. So just because of this, whatever the drag is produced, that is called the vortex drag or induced drag. That is produced at the vortex of the wing only. Next is wave drag. So wave drag is just because of shock or sudden change in velocity. Whatever they will experience the wave that is the wave drag, which is irreversible thermodynamic process. Yes, we cannot reverse it. Whatever is there, they will experience. That's all. Form drag or boundary layer pressure drag. Form drag is caused by the difference between the pressure distribution over a body in viscous flow and that is ideal in viscid flow. Now, just see. Cause difference between the pressure distribution. So at the leading edge, here more area is there, so more pressure will be there, and at the trailing edge, lesser area, so less will be there. So difference between these pressures also create a drag that is called the form drag. Next is profile drag. It's the sum of a skin friction drag and form drag. Already we had seen the skin friction drag because of the skin, and form drag is what? Because of the pressure difference, whatever the drag is produced. That is the form drag. Okay, for reference, you can use these two books. Thank you. If you have any doubt, you can comment on the video or you can directly contact. My contact number is in the first page itself. So you can contact me regarding to that one, and I hope you will complete the assignment for your practice.
Like, share and subscribe. Hit the bell icon for more updates.